Okay, so I'm Santiago. I'm a PhD student at NYU. And today I'll be talking about in-toto. In-toto is the first framework to cryptographically protect the supply chain as a whole, the software supply chain. Now, you may be wondering what a software supply chain is. Well, every single piece of software that you have in your machine right now was made through a software supply chain. For example, here's a very simple software supply chain that's using 4 nodes or 4 servers. You have a version control system. You have a CI system that's running tests constantly against all of the commits in the version control system. You also have a box building, a build farm, or anything really that's building your source code. And then you have your packaging step that takes the binaries and then puts them on a package. This could be a Debian package that's shipped to the users. Now, we're in USENIX Security, so it wouldn't be a surprise for anybody here that things can happen in the software supply chain. Hackers can break into the version control system of a Juniper firewall, flip a pseudo-random seed for the IPsec stack, and be able to decrypt all of the IPsec connections to all of the Juniper firewall boxes. And like this, there has been many other compromises on different systems. The same thing can happen in the build system. Hackers can provide developers a tampered version of Xcode that will produce a backdoored version of Xcode that's shipped into the iOS App Store, and it compromises many of its users. This is, of course, not an isolated incident either. The same thing can happen in the packaging step. You can have a backdoored version of phpMyAdmin sitting on a Korean mirror that's targeting a specific set of people and installing a backdoored version of phpMyAdmin on their box. This is, of course, as you may have guessed, not an isolated incident either. And the same questions arise when we're talking about testing, scrutability, and compliance. There has been a case in which a buggy Windows update was released, and many people were actually suspecting that there was like foul play because it was actually just released to a certain portion of the population in Kazakhstan. As you may have guessed, again, this is not an isolated incident. Now, software supply chain attacks happen, as we have seen, very often. As a matter of fact, the Symantec Internet Security Threat Intelligence Report said that in 2017, software supply chain compromises went up 200%, and in 2018, they went up another 76%. And I'm just stopping here for a second because I want you guys to see that in this very simple, very toy example, side project type of thing, for server software supply chain, you have 8 points in which a simple compromise may be devastating for the end user. And well, I'll be moving on to, well, you know that there's specific point solutions, and we're not trying to fix this. We know that there's a git commit signing that can prevent hackers from tampering with the version control system. There's things such as reproducible builds that can help you from backdooring compilers. There's projects such as Notary and Tough that are protecting users every day. Now, even with those, there's the element of, well, is the security policy actually in place? Is it actually being followed? Is this product actually being shipped into the next step? And is this security policy the same or as was expected, and so on and so forth? Now, this is why we came up with in-toto. We're trying to rethink a way to protect the software supply chain as a whole. We do this with 3 major principles. The first one is compromise resilience. We know that it's possible that attackers will break into individual nodes, and we want to minimize the impact. We do this through 2 techniques. One of them is role separation, and the other one is having revocation and key rotation as a primary, as first-class primitives. The second one is we want in-toto to be all-encompassing. We want to protect from all the way to the left and to all the way to the right, from the moment the first line of code has been committed all the way into the end user installation of the device. We do this through 2 very simple properties. One of them is being tool-agnostic that allows us to be seamlessly integrated in any supply chain. And finally, we don't want to enforce any type of use, and we want our system to be expressive enough to be adopted everywhere. I'll elaborate a little bit on this. So we have this software supply chain again, and we know that there's 4 actors operating on it. We have Bob that's tagging a git release. We have Carl that's building. We have Erin that's packaging everything together. And then we have Dave that's testing. We know that compromises happen. And so it happens that Dave is compromised. We want that even if Dave is compromised, we're able to still provide some degree of security on the resulting package. And we also want to be able to take Dave's key out or Dave's privileges to test and replace it with, say, Ada, that we trust that she can actually perform the tests correctly. The second principle is being tool agnostic. We know that this is a very common supply chain. We know that many of you recognize some of the logos here. But we also know that you may recognize Mercurial. Many types of software are built using different version control systems. And by being tool agnostic, we're able to be all-encompassing, which is the third property that we're looking for. Now, today, this is how a software supply chain looks in the toy example. Tomorrow, it could be anything else. And I'm trying to go like all the way out here. And let's think that Gene Sudik came out with a fingerprint reader-enabled authorization system for every single line that has been written. And we want in-toto to be able to wrap and authorize the operations done in that specific step of the supply chain. And thinking of like farther down, I'm going crazy here. Let's say that Gene Sudik came out with an Hypno attack in 2021. And on 2022, he also came out with a USENIX Security paper that detects the intent of people so that we know that even if they're hypnotized, they're not committing anything malicious into the server. Well, we want that to be also be able to be protected using in-toto. So this finally leads us to this like expressive property that lets us pretty much protect any supply chain out there in existence. And we've actually seen that we can represent any supply chain using our very simple domain-specific language and our very minimal schema. So I'm going to explain how we do this. We have 3 main goals. One of them is we want to verifiably say what needs to happen, what are the steps in the software supply chain. The second one is we want to verifiably define who's allowed to make this happen. We want to define the authorized actors in the software supply chain. And finally, we want to provide a tight binding between the servers or the nodes in the software supply chain. This is a chain after all, and we want to make all of the links connect together properly. So the first element of in-toto is policy language, what we call an in-toto layout, that basically contains the steps, what needs to happen. It also defines the public keys and the actors. We call them functionaries. These are the people that are allowed to perform operations in the supply chain. Then we also have a way to describe how the artifacts, the inputs and outputs of every single step. It could be source code, it could be binaries, it could be container images, it could be packages, it could be PNGs, it could be anything. We describe how this relate to the steps themselves. And finally, we provide an extension to the language to be able to tie this together. We want to say that if there's a tag release with a version of the source code, it's the same one that's used as an input in the CI system. And it's exactly the same one that's input into the build system, and so on and so forth. Now, we also want to have an authoritative source of this policy, so we expect this to be signed by a project owner. In practice, and we'll see later, this could be a release manager, this could be a security team, this could be the benevolent dictator for life on an open source project. Now that we know what needs to happen, the next element that we need is information about what happened. So we built a very simple toolchain that pretty much wraps any single possible process or operation. And this produces attestations. These attestations are signed with private keys of the functionaries in the supply chain. And they provide information about the host. They provide information about the materials that they used, the products that they created, and any other useful information like standard input, standard output, and so on. With this, we can actually verify that the software supply chain has been its integrity has been not violated. We use 3 elements. We use the artifact that you're going to install. Back in our example, it could be a Debian package. We have our policy, and we have a series of attestations of the operations that were performed. Then the verification is simple. We want to make sure that all of the attestations form a graph, and does this graph look like the graph that we have described in the policy language. Now, we know that this verification can pass. Now, we want to make sure that this actually protects against compromises that we have seen in the wild. Well, we have a very simple, very minimal threat model. It's very encompassing, but it's very easy to follow. We assume that anything can be compromised because we have seen that everything has been compromised in the software supply chain. Core infrastructure, such as version control systems, package repositories, testing infrastructure, build machines, all of that can be compromised. We also assume that the communication channels between all of these servers can be also compromised. So if something is floating on an HTTP connection, they man in the middle it, they flip a bit, and you're also compromised. And we also assume that the attackers can compromise developer keys or functionary keys or compel functionaries into signing different operations. Just for the sake of keeping the security analysis simple, I'm going to ignore this for a second, and then we'll get back to it. So to quickly follow this we know that the policy cannot be changed unless the functionary key, the product owner key has been compromised. So they cannot define new steps, or they cannot remove steps, or provide incomplete final products. We also know that these operations are all the operations that need to happen because they're described in the policy. And unless the attackers are able to compromise developer keys, they won't be able to produce attestations on behalf of these functionaries. And since there's a hash chaining mechanism that makes sure that the artifacts that were produced and consumed throughout the chain haven't been tampered with, attackers cannot change the artifacts as they flow through the chain. Now, going back to key compromise, we assume that attackers can actually compromise keys. If the attacker can compromise fewer than a threshold, we're back to the example before. If an attacker can compromise functionary keys, the effect will be pretty much scoped by the domain-specific language that we produced. And if more than a threshold of project keys, say that many keys of the functionaries have been compromised or the project owner key has been compromised, then we're pretty much back to step 0. This is a compromise as if in-toto didn't exist. Now, this is a table from the paper. I invite you guys to read it, but it's basically just to point out the 3 elements that are in play. If you compromise a key from a functionary that's in which the domain-specific language allows them to create something, and that something that's created is being used further down, then the attacker can tamper with an artifact that we call that product modification. And that's scoped under the specific patterns that the domain-specific language will define. Now, to ground this a little bit more in reality, I wanted to go through the integrations. in-toto is being used pretty much everywhere. It's inside of thousands of companies today. And you may be protected by this, and you don't even know it, which is like the good thing of security products. I will go into the Datadog example, which actually encompasses a bunch of all of these other users. Datadog is a cloud observant agent. It's a metrics system. And to do so, it installs an agent inside of all of the different servers in the cloud. This is very critical because if this agent were to be compromised, then, well, it could do devastating damage to all of these companies that you saw before. In order to the Datadog agent to understand the different workloads in the cloud, they have something they call integrations, which are pretty much translation layers between the workloads, like a MySQL workload or an NGX workload or an Amazon AKS workload. And these translation layers are installed into the different agents that are running these workloads in the cloud. Now, these specific integrations are the ones that are protected within in-toto. And they use this very simple software supply chain to produce the integrations. They have developers produce the source code. They use a hardware token, and they actually need to physically touch a hardware token every time they commit a new version of the integration. And then this is pushed into an untrusted CI and CD system that's creating these attestations as well as the things follow through. Finally, this is all pulled by the agent, and the agent inspects that all of the sources that came in the package actually came from authorized actions by the developers or the CI. This actually this actually was pretty cool because we found out that vulnerabilities on zip extractors cannot affect this integration, because even if you're able to bypass paths or change the sources of everything, the agent will be able to track back all of the sources and all of the paths to the original source that was the developers using hardware tokens. Now, this is how it's used today. We use all of the information from the Datadog deployment in order to explore how costly or how how in-toto would perform. We also explored how software supply chain compromises that have happened in the last 3 years would affect in-toto. We found out that depending on how you define the policy, some of them would apply, some of them would not be protected, but most of them, more than 3/4 of them, would be prevented by in-toto. We also checked out the metadata cost. Sometimes it oscillates between 20 and 30%. There's special edge cases that are mostly due to test files. But in general, it's just a couple of kilobytes. So users don't mind paying the cost for the benefit of protection. And just to conclude, in-toto is a novel supply chain mechanism that uses 3 principles to protect the software supply chain. One of them is compromise resilience. The second one is it being all-encompassing, being able to protect everything. The third one is it's expressive enough to actually represent any supply chain in existence. We're through this, we're able to protect thousands of organizations and companies, and we're a vibrant community of 30-something contributors today from 10 different organizations, including Google, Red Hat, IBM, and some others that I cannot mention. We invite you to the Linux Foundation CNCF KubeCon Santiago in November 18 to 21. We're actually now part of the Linux Foundation. We're under a nonprofit organization. We're actually hoping that we will become the standard for exchange of software supply chain information in the future. And finally, I wanted to thank all of my contributors, all of the people that made this a reality. It's been a 3-year-long process to make this project be out there, protecting everybody. And with this,
thank you.
Hi, Kapil Singh from IBM Research. Very interesting talk. One question I had is, how do you incentivize different supply chains? For example, if you are, a lot of work is you use open source from different sources, how do you make those developers write the policies you require? And we are talking about millions of libraries out there. Red Hat, you mentioned Red Hat. Red Hat's one of the business model is to and verify those libraries. So how do you incentivize verification of those libraries and writing the code or the policies you require from the developers of these open source libraries?
Well, that's a good question. There's a lot to do with the economics of open source, but I can tell you that we are actually available in Arch Linux and in Debian, and we're actually, if you read the paper, you'll see that there's an in-toto transport to verify reproducibility of builds in your Debian packages today, using different rebuilders across like academia and nonprofits and others. I think that since this is becoming more and more of a threat, people are starting to awake and go, hey, we need to actually take care of this. We are working with other big companies that want to push, one of them is Red Hat, want to push this to be a standard so you can essentially pull in an open source package that has all information about the policy that was followed, and you can introspect into it and decide whether you're going to use it or not. I don't know what's the best way to push people towards it. I just think it will become a reality.
Thank you.
No problem.
Hey, this is really really cool, and I was wondering if you'd given some thought to how this might actually also hook in future to the sort of the what is operating in the system, what software is running in the system, and attestations of what's operational, right? So you already have some sense of of the supply chain of where the software was produced, and now maybe as you're running your system administrator, you want to know that the things you thought you had are actually running in the system, hooks into what's going operationally, how you attest to that, and how you use some of what you've produced to do that. Given any thought to that?
So I'll try to answer as fast as I can because we're over. But there's, you can recursively verify using in-toto. So you can take a part of the tool chain and say, hey, this part of the supply chain needs to be verified further down. And the other is you can use hardware-based attestations to provide state of the system before you run all of the executions. That's part of future work that we're looking at. We're going to call this functionary in a box.
Okay. Thank you very much. And of course, we now know some of what Gene Sudik is working on.